As the Earth's population grows and demands for comfort and newer technologies increase, more and more chemicals are produced and used in various combinations. Many of these chemicals reach the Earth's atmospheric layers, producing different types of pollution. Some of these chemicals make up the refrigerants that cool or freeze our food and cool our homes, office buildings, stores, and other buildings in which we live and work. Many of the refrigerants we use were developed in the 1930s. While contained within a system, the refrigerants are stable, are not pollutants, and produce no harmful effects to the Earth's atmospheric layers. Over the years, however, quantities have leaked from systems and have been allowed to escape by the willful purging or venting of systems during routine service procedures. Ozone is a gas that is found in both the stratosphere and troposphere. Figure 9-1. Ozone is a form of oxygen gas whose molecule consists of 3 oxygen atoms, O3. Figure 9-2a. The standard oxygen molecule that we breathe is O2. Figure 9-2b. Stratospheric ozone, which resides 7 to 30 miles above the Earth, is considered good ozone because it prevents harmful ultraviolet UVB radiation from reaching the Earth. Tropospheric ozone, however, is considered unwanted ozone because it is a pollutant. Stratospheric ozone is formed by the reaction that occurs when sunlight interacts with oxygen. This ozone shelters the Earth from UVB radiation. This protection is essential for human health. Stratospheric ozone accounts for more than 90% of the Earth's total ozone and is rapidly being depleted by man-made chemicals containing chlorine, including refrigerants such as CFCs and HCFCs. The troposphere, or lower atmosphere, that extends upward from ground level to about 7 miles, holds only about 10% of the total ozone. The troposphere contains 90% of the atmosphere and is well mixed by weather patterns. Sunlight acting on chemicals in the troposphere causes bad ozone. This ozone has a bluish color when seen from Earth and may irritate mucous membranes when inhaled. A popular term for tropospheric ozone pollution is smog. Once stratospheric ozone is formed, much of it is easily destroyed by the sun's ultraviolet radiation, which is very powerful and has a frequency almost as high as that of X-rays. The sun's radiation will break down the ozone, O3 molecule, into a standard oxygen, O2 molecule, and an elemental free oxygen, O molecule. Figure 9-3. At the same time, more ozone is produced through photosynthesis and the bonding of standard oxygen, O2, with free oxygen, O. Ozone is constantly being made and destroyed in the stratosphere. This balance has been going on for millions of years. However, man-made chlorine-containing chemicals have knocked this delicate process out of balance in the last couple of decades. Once in the stratosphere, ultraviolet radiation will break off a chlorine atom, Cl, from the CFC or HCFC molecule, figure 9-4. The chlorine atom destroys many ozone molecules. One chlorine atom, Cl, can destroy up to 100,000 ozone molecules. The depleted ozone molecules in the stratosphere let more UVB radiation reach the Earth. This causes an increase in skin cancers, an increase in the frequency of cataracts in humans and animals, a weakening of the human immune system, and a decrease in plant and marine life. An index called the Ozone Depletion Potential, ODP, has been used for regulatory purposes under the United Nations Environment Programme, UNEP, Montreal Protocol. The higher the ODP, the more damaging the chemical is to the ozone layer in the stratosphere. When stratospheric ozone intercepts ultraviolet light, heat is generated, figure 9-5. This generated heat is the force behind stratospheric winds, which affect weather patterns on Earth. By changing the amount of ozone, or even its distribution in the stratosphere, the temperature of the stratosphere can be affected. This can seriously affect weather here on Earth. Global warming. Most of the sun's energy reaches the Earth as visible light. After passing through the atmosphere, part of this energy is absorbed by the Earth's surface, and in the process is converted into heat energy. The Earth, now warmed by the sun, radiates heat energy back into the atmosphere towards space. Naturally occurring gases and tropospheric pollutants like CFCs, HCFCs, and HFCs, as well as carbon dioxide, water vapor, and many other chemicals, absorb, reflect, and/or refract the Earth's infrared radiation and prevent it from escaping the lower atmosphere. Figure 9-6. These gases are often referred to as greenhouse gases. This process slows the Earth's heat loss, making the Earth's surface warmer than it would be if this heat energy had passed unobstructed through the atmosphere into space. The warmer Earth's surface in turn radiates more heat until a balance is established between incoming and outgoing energy. This warming process, caused by the atmosphere's absorption of the heat energy radiated from the Earth's surface, is called the greenhouse effect, or global warming. The direct effects of global warming are created by chemicals that are emitted directly into the atmosphere. These direct emissions are measured by an index referred to as the Refrigerants Global Warming Potential, GWP. Refrigerants leaking from a refrigeration or air conditioning system contribute to global warming. These direct effects of global warming are measured by comparing them to carbon dioxide, CO2, which has a GWP of 1. Carbon dioxide is the #1 contributor to global warming. People have increased the amount of carbon dioxide in the atmosphere in excess of 25% of its usual amounts. Most of this increase is through the combustion of fossil fuels. This combustion of fossil fuels is caused by the need for electricity in our modern world. In fact, much of this electricity is generated to power refrigeration and air conditioning equipment. The more efficient the HVACR equipment is, the less electrical energy that is needed. Even refrigeration or air conditioning equipment with a relatively small charge of refrigerant that never leaks out may have a great impact on global warming if the equipment is undercharged or overcharged. The equipment would be very inefficient under these conditions, and the carbon dioxide generated from the longer run times created by these inefficiencies would contribute to global warming more than the refrigerant leaking out. This is an example of an indirect effect of global warming. In the HVACR industry, these indirect effects of global warming are what concern scientists. Most of the newer refrigerants introduced to the HVACR industry are more energy efficient than the ones they are replacing. However, some are not as efficient. Even though some of the newer refrigerants do not contribute to ozone depletion, they still can contribute to the direct and indirect effects of global warming. An example of this would be the newer refrigerant HFC 134A. It has a 0 ozone depletion index and contributes to global warming directly via a refrigerant leak and indirectly through being used in an inefficient system, with a longer runtime that is caused by the refrigerant leak. The total equivalent warming impact, TEWI, takes into consideration both the direct and indirect global warming effects of refrigerants. Refrigerants with the lowest global warming and ozone depletion potentials will have the lowest TEWI. Using HFC and HCFC refrigerants in the place of CFCs will also reduce the TEWI. All of the newer refrigerant alternatives introduced have a much lower TEWI.